The solution to a system of linear inequalities, if a solution exists, always takes the form of a graph with a shaded region. Before we get into solving a system though, let's just do a quick review of graphing a linear inequality. To start off with, we can make sure we're keeping in mind what we refer to as slope-intercept form for an equation. Rewriting equations in slope-intercept form is convenient because whatever that value for b is, the constant isolated by itself, is the y-intercept for our graph, and whatever our value for m is, whatever that coefficient in front of x is the slope of our line. There are different ways to approach graphing inequalities, but what we're going to do is look at taking each inequality statement and first rewriting it as an equation. So 3x plus y is greater than or equal to 9 becomes 3x plus y equals 9. Solving for y means we would subtract 3x to the other side, giving us an equation in slope-intercept form. To continue graphing this equation, or graphing this inequality, what we can do is start by first plotting a point at that y-intercept, 0, 9, and then using our slope of -3 to tell us that we would go down 1, 2, 3, and then over 1 to find our next point. We could continue to repeat that to find additional points, and then draw the line represented by that equation. So what we've graphed is the line y equals -3x plus 9. What we're actually looking to graph though is this inequality statement. One thing to keep in mind right now would be that if our original inequality statement was something like 3x plus y is strictly greater than 9, we would actually want to have graphed that line as a dashed line, representing that the points along that line itself aren't solutions. But in this case we had a greater than or equal to statement, so we use a solid line. And the next step is to determine which side of the line we should shade on. To do that, we'll look at a couple of test points, which can be any points that aren't located on the line itself. 0, 0 is always a nice, easy test point to use, as long as our line doesn't pass through that. And then on the other side of the line, we can look at the point, say, 5, 5. To test these points, what we'll do is plug the values for x and y into the original inequality statement and see if it makes that inequality true or false. So first off, we would get 3 times 0 plus 0 is greater than or equal to 9, which would mean 0 has to be greater than or equal to 9, which is clearly false. So we can look at using our second test point, 5, 5. Again, we'll plug those values for x and y into our original inequality statement. To give us 15 plus 5, or 20, is greater than or equal to 9, which is true. So that means that any points on the same side as 5, 5 for this line will be solutions to the original inequality statement. To represent those infinite solutions, what we want to do is just shade everything then on that side of this line. Again, indicating the shaded region and our solid line represent all of the solutions, all of the different xy pairs that would make this original inequality statement true, and any xy pair on the other side of that line represent xy pairs that would make this inequality statement false. So for shading an inequality statement, we always need either a solid or dashed line, and then we're going to look at shading one side of that inequality statement or the other. depending on which side contains points, which makes the inequality true.